Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at reliability and flow control. We'll be discussing TCP reliability with guarded and ordered delivery and data loss retransmission, and we're going to talk about TCP flow control with window size and acknowledgments, maximum segment size, and congestion avoidance. This episode is part of my series on Introduction to Networks for the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. TCP can handle what we call the flow control to make sure that the devices don't get overloaded when they send data. The example of this would be if the destination happens to be an older computer or only has a 10 meg connection and your computer is a newer computer and it has a gig connection. We are not going to send that information out at gig speeds. We're going to send it out at 10 meg speeds because that is all the destination can handle. And sometimes through the process of data traveling through the network, it takes different paths, takes different routes through the network. Maybe it becomes corrupted and needs to be retransmitted. Segments arrive out of order. When these segments arrive out of order, the TCP takes care of reordering them and putting them in the correct sequence. They do this based upon a sequence number that's in the header of each packet. What we're going to do is we're going to take a look at the TCP operation, but we're going to take a look at it in a simplified process. And this may not be a realistic depiction, but you'll get the overall concepts down on how this process works. Remember, TCP is a connection-oriented protocol. In that, a connection is established first using that three-way handshake before data is sent. Another characteristic of TCP is that it is a reliable protocol. There are two things that make it reliable. Those two things are sequence numbers and acknowledgments. Every TCP segment that is sent in a TCP conversation gets a sequence number. So every byte of data is numbered basically in a sequential list. This allows the receiving host to rebuild those segments according to that sequence number. If data arrives out of order at the receiving end, the data can be put together back in the proper order thanks to the sequence numbers. Acknowledgments come into play by helping the sender know that the data being sent is actually being received. The way this works is the sending host sends TCP segments, bytes, and the receiving host acknowledges those bytes by sending acknowledgments. There is a limit to the amount of data the sending host can send before it receives an acknowledgment from the receiver. This amount is called the window size. The window size is the total number of bytes sent in TCP segments that can be sent before receiving an acknowledgement. Using TCP window scaling, computers are able to achieve large window sizes of up to 1 gigabyte. As the sending host sends bytes of data in TCP segments, the receiving host returns acknowledgments as it processes bytes received and frees up its buffers. We can see this depicted in this graphic. Let's start by reading the message sent by the sending host. That's right here. Start with byte number 1. I am sending 10 bytes. In this scenario, the 10 bytes, those 10 bytes right here, that's the window size. In reality, the window size would be a lot larger than 10 bytes. Since today, window sizes are typically 60 megabytes or more. But this works for this example. The host is sending 10 bytes, starting with 1. The receiving host, the server over here on the right side, the server says right here, I received 10 bytes starting with byte number 1. I expect byte 11 next. This here, that is the acknowledgement, what the server said. The server acknowledged it received those 10 bytes and is now expecting number 11. If we look down here at the bottom, we can see here in the first segment, right there, starting with sequence number 1, 10 bytes have been sent. Right there, we've sent 10 bytes. The receiver sends an ACK 11, an acknowledgement 11. Starting with 1, 10 bytes were sent. So the next sequence it's expecting is an 11, and that's in our acknowledgement. This acknowledgement is sent back to the originating host, right there. Now the originating host sends 10 more bytes starting with number 11. If you were to ask yourself, what would be the next ACK, next acknowledgement that the server would send back to the originating host, we would have to ask ourselves, what is the last sequence number sent? Starting with 11, 10 bytes were sent. So the last sequence number that was sent was number 20. So that the ACK that the server would send back would be a 21. That is the next expected sequence number. You can see how sequence numbers and acknowledgments, including the window size, makes TCP a very orderly and reliable protocol. I hope you're liking this episode on reliability and flow control. If you have the time, please leave a comment and let me know what you think about reliability and flow control. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. No matter how good you build your network, you're going to lose data across your network. That is just going to happen. And TCP has mechanisms in here to help us identify that data loss and retransmit the missing data. Now, TCP, what it does here is it sends out data up to our window size. And once again, for this example, we're going to use a window size of 10 segments. That's all we're going to be able to send out is 10 segments. And it's going to wait for acknowledgments to come in. As you can see in this graphic right here, PCA is sent out 10 segments to window B. And in the next graphic to the right here, PCB has sent back an acknowledgement of 1, saying it received it. Then it sends back an acknowledgement of 2, and then it sends an acknowledgement of 3. And once again, what that acknowledgement says is the next packet I'm expecting is 3. And it's waiting and waiting. It's going to reach its timeout feature, and then host A is going to resend that information. And how this works is, what it's going to do is host B is still waiting for segment number 3. It's going to retransmit 3 and everything else it's sent out in that window. It assumes if 3 didn't make it, the rest of it didn't make it. In actuality, if we look at our graphics, that only segments 3 and 4 didn't make it. Segments 5, 6, 7, 8, 9, and 10, 5 through 10, they made it through. But because host A sending the acknowledgement says, I'm waiting for segment 3, it's going to send 3 all the way to the end of that window that we have transmitted. So it's going to send out 3 through 10. 3 through 10 is going to broadcast 3, 4, 5, 6, 7, 8, 9, 10. It retransmits 3 and 4. Those were the 2 that was lost, but it's also going to retransmit 5 through 10. And that's going to be duplicate segments, taking up resources on your network. If both ends of the devices support SAC, and what SAC is selective acknowledgement. That's negotiated during that 3-way handshake. Selective acknowledgement identifies which segments have been made, or which segments have made it through, which segments have got acknowledgments coming back, and then let's retransmit the missing ones. And we can see here in this example, we send out our 10 segments again. PCA sends out 10 segments. All of them make it through except 3 and 4. And host B here sends back here an acknowledgement that says, I'm waiting for segment 3, but I'm also going to send back a selective acknowledgement saying I got segments 5, 6, 7, 8, 9, and 10, and got 5 through 10 in there. And then host A sends segments 3 and 4. Notice it's got an acknowledgement that says I'm waiting for segment 3. The selective acknowledgement says I received 5 through 10, so it's missing 3 and 4. It resends 3 and 4, and then it sends a couple more because our window is open. We can send more data. That's how TCP works when you have selective acknowledgements. Let's work through an example of data loss and retransmission. Now, in this example, we're going to use segment numbers, where in actuality TCP uses segment numbers, but we're going to use segment numbers. It helps us more easily understand what is happening. Remember that TCP is a reliable protocol. It uses sequence numbers and acknowledgements to provide that reliability. But what happens when data is lost in transit? As a reliable protocol, there has to be a mechanism to retransmit lost data so that an entire piece of data, like a file or an image or a video, can be rebuilt from all of the segments. Let's go through this process in action. The source host here sends segment 1 and starts a timer. That first segment goes from the source to the destination, and the destination receives that segment, and that timer continues to run. And the destination receives segment 1, and because it received it, it's going to send an acknowledgement. We can see that the destination has received segment 1, acknowledges the delivery, and is going to send an ACK 2 requesting segment number 2. Why? Because it received segment 1 and now it's going to request segment 2. The acknowledgement goes back to the source. The source receives that acknowledgement before that timer expires, and now it can send segment 2. Segment 2 is sent, but it is not received. And it's going to wait to get an acknowledgement for segment 2. If it does not receive an acknowledgement from the destination before that timer for segment 2 expires, it's going to resend segment 2. So timer for segment 2 has expired. The destination receives segment 2. This time the information was received while that timer for segment 2 continues to run. And now the destination is going to send an ACK 3. Once again, that ACK 3 is a request for segment number 3, basically acknowledging it received segment 2. Now I'm waiting to receive segment 3. Then the source receives acknowledgement before segment 2 timer expires, and segment 3 is sent and starts the timer for segment 3. Segment 3 is received. Destination sends an ACK 4, which says, I'm waiting for segment 4, thereby acknowledging it received segment 3. And the source now receives that acknowledgement for segment 3 while the timer is still running, so we don't have to resend that data. And this process continues until all the data has been sent, and then we end the transmission. We go through that process of that ending double two-way handshake. TCP provides mechanisms for flow control. Once again, flow control is the amount of data the destination can receive and process. And so it only can receive a certain amount of data, and we want to make sure that we don't overload it. TCP helps maintain that reliability by adjusting the rate of data flow between the source and the destination. It allows the destination to communicate how fast it can process that data, and we're not going to overload it. The maximum segment size, or MSS, is the amount of data the destination device can handle. Typically, for IP version 4, the MSS is 1,460. And what that is the host determines the value by subtracting the IP address and TCP headers from the Ethernet maximum transmission unit, which is 1,500 bytes by default. 1,500 minus 20 bytes for the IP version 4 header minus 20 bytes for the TCP header, that gives us our 1,460 bytes for our maximum segment size. TCP also does congestion avoidance. And what happens here is PCA is sending data to PCB. PCA then thinks to itself, hey, I'm not getting the acknowledgments I'm expecting from PCB. What I'm going to do is I'm going to slow down the number of bytes that I'm sending out before I get acknowledgments. Just slowing down the amount of data I'm sending through the network. There's some sort of congestion on the network that is causing my data not to get delivered. I'm not getting my acknowledgments back, so I'm just going to slow it down. It was my pleasure to provide you with this wonderful episode on reliability and flow control. If you like this episode and you got value out of it, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on Introduction to Networks for the CCNA. In the bottom right is one of my favorite videos that I linked just for you. Thank you so much for watching this episode of my series on Introduction to Networks for the CCNA. I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.